Hello, I'm Dr. An. In this video, I'll tell you what you have to use for the basic measuring units in science. And most importantly, you will learn how all these units are defined. It's a very interesting topic, so stay tuned. There is a circle chart that summarizes 7 base units from which other units are derived. And these 7 units are defined by using these corresponding fundamental constants of nature. Let me separate these 7 pieces apart so that I can explain better. The darker colored outer circle components are abbreviated units, and these lighter colored components inside the circle chart represent fundamental constants of nature by which each unit is defined. These 7 base units are time in seconds, length in meters, mass in kilograms, light intensity or luminous intensity in candelas, the amount of substance in moles, temperature in kelvins, and finally electric current in amperes. Now here's what's really important. Look at all these numerical values that are representing the entities with lighter colors in the chart. Well, these are the constants that represent scientists' 150-year dream of a measurement system based entirely on unchanging fundamental properties of nature. And it happened in November 2018, very recently. Let's begin with time. Base unit of time is a second with abbreviation S. And here is the current definition of time. It is defined by taking the fixed numerical value of the cesium frequency, the unperturbed ground state hyperfine transition frequency of the cesium-133 atom, to be this number when expressed in the unit of hertz, which is equal to 1/2. Well, if you understand what they're talking about here, I admire you. But for most of us, here is a more down-to-earth definition. 1 second is the time it takes the cesium-133 atom to release exactly this number of cycles of microwave radiation when making its hyperfine energy transition. Still pretty hard to grasp, but it basically says we're counting the number of cycles of light wave radiating out of the cesium atom during something called hyperfine energy transition. So if we count this exact number of cycles, which is over 9 billion cycles, that's 1 second. Now let's take a look at the accuracy of these atomic clocks. It gives you a less than 1 second error in 300 million years. If you think this is incredible, let me tell you what they're currently up to in order to even improve this atomic clock machine. Before I do that, this is the picture of the cesium atomic clock back in 1959. It's called NBS-1 machine. And these 2 pictures show somewhat current clocks that scientists are working on, and I got these pictures from the official site of NIST. Now, as I mentioned, there are other more advanced and improved models of clocks scientists are working on. And one of them is called a strontium optical clock. By the way, let me show you where these cesium atoms and strontium atoms are in our periodic table. Here is a cesium atom, here is a strontium atom. They're all on the left side of the periodic table because you want some simplicity of electrons in the outermost shell to make energy level transitions measurable. Now, how accurate is this future optical clock? Are you ready? You will have less than 1 second error in 13.8 billion years. That's almost time from Big Bang until now, according to scientists. Let me address one of the astonishing consequences of having this crazy accurate clock. Einstein's general theory of relativity tells you that if you are in higher elevation, time passes slower because the gravitational acceleration is lower as you go higher from the ground. So if you can have this insane accuracy of future optical clock, you can actually prove the Einstein's general theory of relativity that if you go up by 10 centimeters, they can detect the time slowing. Is this crazy or what? And of course, we wouldn't be able to notice any difference in our daily lives. We're talking about an accuracy of 1 second error in almost 14 billion years. Let's go to the next SI unit, length, and its unit is meter. This is the current definition adopted back in 1983. It is defined by taking the fixed numerical value of the speed of light in vacuum, c, to be this number when expressed in meters per second, where the second is defined in terms of this transition frequency. Let me write this definition in a little bit more friendly way. Well, based on the definition of 1 second, 1 meter is defined by the speed of light. And here's the definition. 1 meter is the distance the light travels in this fraction of seconds in vacuum. And let me just elaborate a little more. Well, since speed is distance over time, distance is speed times time. And the speed of light is defined to be exactly this number, which is extremely fast. But if you measure its travel time for this crazy fraction of second, which is the reciprocal of the speed of light, then voila, the light just traveled 1 meter. And that gives you the definition of 1 meter. Now let's move on to the mass. These are the small cylinders of platinum iridium alloy that all of us have been relying on for the definition of 1 kilogram. Among all the SI units, the definition of kilogram was the only unit that depended on physical objects or physical artifacts. All other units had their definitions based on atomic levels with the help of quantum mechanics. And finally, as of 2018, the mass has been redefined so that it also can have its definition based on nature's unchanging constant. The original cylinder that have been preserved in the outskirts of Paris and all other duplicate cylinders around the world, RIP, rest in peace. They served us good for more than a century. Okay, let's take a look at our new definition of 1 kilogram. It is defined by taking the fixed numerical value of the Planck constant. Okay, by the way, this is one of the most intimidating definitions you'll ever see. Well, you're welcome to read this, but let me give you my interpretation of this formal definition. And I did my best, trust me. 1 kilogram is the mass that can be obtained by E equals mc squared and E equals h nu, where h is defined to be this number. Well, the mass was just redefined in 2018 this way, but the key to our ability to get rid of this physical cylinder to define the mass has been with us ever since Einstein came up with his famous and majestic formula, E equals mc squared, back in 1915. With his theory, a physical entity mass can be converted into energy, which has been all proved by atomic bombs and hundreds of nuclear power plants all over the world. So mass can be converted into energy, and that energy is in turn related to this Planck constant h times the frequency of the light nu. So if you let those two equations equal to each other, we have mc squared equals h nu, and therefore we have m equals h nu over c squared. Since we know all the quantities on the right side, the mass 1 kilogram is defined. I simplified this whole definition to the level that average physics students can understand, but if you want to understand the definition in the full scope, you will need to learn much more advanced physics, including Einstein's general theory of relativity. Let's move on to luminous intensity, or you can call it light intensity. The unit is candela. It's a long definition, and I'm going to skip reading. But if you see a case of new light bulbs at home, please grab one and take a look at what information you have on the outside. It gives you information on its brightness in lumens, not in candelas. Well, that's because the candela is more of a base unit defined, and lumen is the derived unit that measures the brightness of three-dimensionally radiated light. So in our daily lives, lumens make more sense. But the definition of lumen is based on this base unit, candela. Let's spin the wheel. Next one is your best friend if you like chemistry. Amount of substance in the unit of mole. A mole contains exactly this number of elementary entities, which is the fixed numerical value of the Avogadro constant. Well, this is another big change. As of November 2018, we're not going to be using carbon-12 to define the mole anymore. Instead, we fixed the Avogadro number as Avogadro constant, and it's not an approximated number anymore. It's an exact number, just like any other constants we use in this SI circle chart, such as Planck constant and Boltzmann constant. Well, Boltzmann constant, we're going to be hearing this in the next SI unit, which is temperature. Well, sorry, international standard unit for the temperature is neither in Celsius nor in Fahrenheit. It's in Kelvin. If you want to relate our Fahrenheit to Celsius, this is the formula. And Celsius to Kelvin, this is the formula. We use Kelvin almost only in the scientific community. And this is scientifically more sound measurement of temperature because 0 Kelvin is determined by extrapolating the ideal gas law, as I show here. And here is the current definition. The Kelvin is set by fixing the numerical value of the Boltzmann constant to be equal to exactly this number. Well, of course, to a lot of us, it doesn't explain directly what 1 Kelvin is. So let me restate the definition in a little easier way again. Here we go. 1 Kelvin is equal to a change in the thermodynamic temperature that results in a change of thermal energy by exactly this many joules. Well, if I cut it shorter and make it more simplified, here we go. 1 Kelvin raises the thermal energy by exactly this many joules. All right, finally, the last 7th base SI unit, electric current, and its unit is in ampere. The ampere is defined by taking the fixed numerical value of the elementary charge E to be exactly this number when expressed in the unit coulomb. Well, this is again a major change from the previous one. This new definition in 2018 is actually defining the elementary charge to be this exact number, instead of backtracing what it was after measuring the current, which created an approximate number for the charge. If I translate the above definition, the charge of 1 electron is defined to be this exact number of coulombs. In other words, if I take the reciprocal, 1 coulomb is defined to be the electric charge of this many electrons. Since the reciprocal gives you non-terminating decimals, we'll have plus minus 1 electron error in 10 to the 18th power many electrons, which is mathematically 0 error. And therefore, 1 ampere can be defined because it's simply 1 coulomb of electric charges passing per second. Now, in the physics community, there has been a hot debate whether the ampere should be changed to derived unit and the elementary charge E must be a base unit instead, since the electric charge E is defined to be an exact number in 2018. Well, all these debates are summarized in one simple sentence posted in the NIST official website. And let me read that. Although the new definition has finally put the ampere on a more rational footing, it poses new and formidable challenges for measurement science. Okay, this concludes my presentation of 7 base international standard units. And based on these, we have numerous derived SI units with specific names. For example, frequency, force, energy, power, electric charge, electric potential difference, electric resistance, and many, many more. All right, we're done with the units. I'll see you in the next video.